Hello, everyone. We are Group 19. My name is Jason, and along with Joel, Raihan, and Varun, we're here to demonstrate our final year thesis. Have you ever wondered how easy it is for you to interact with a computer or any kind of device? In our day to day activities, we make use of our hands in pretty much all instances, and we generally don't think much of it. But for a paralyzed person, uh, this isn't the same. The only way that a paralyzed person can communicate is through their thoughts. Hence, it becomes difficult for them to interact with the computer. In light of this, we arrive at a solution known as the brain computer interface. A brain computer interface records EG data from the scalp and decodes it to perform an action that the user wishes to. Our thesis aims to present a BCI system that enables a paralyzed person to move a computer. We observe and classify motor imagery signals for horizontal cursor control. We use ERRP signals classified by a separate ERRP classifier to improve the motor imagery classifier. And we also use an ERRP signal generator for data augmentation. Next, we have our methodology.
So BCI uses two classifiers, that is the motor imagery classifier, which is decodes left or right hand imagination, that is whether the user wants to move the cursor to the left or to the right. Whereas our ERRP classifier detects if there is ERRP data that is present in our EEG signals. So ERRP, or error-related potential, is a potential that is automatically evoked in the user's brain when the cursor moves in the wrong direction, or when the user sees that the cursor is moving in the wrong direction. So ERP data sets are not readily available online. And so we use a variational autoencoder to augment our data set and improve it. So the ERP data, the ERP classifier corrects the motor imagery classifier, which is called online adaptation, whenever the user sees that the cursor is moving in the wrong direction.
So I will quickly go into a few details of the process. So when the user thinks of his left arm, the cursor is supposed to move left, and the user thinks of his right arm, so cursor is supposed to move right. So how we do this is something called motor imagery signals, and how the brain looks when the user thinks of either arm. And so the steps that the classifier takes in detecting if a user thinks of his left or right arm is done through a process known as spectrally weighted common spatial pattern, and that really just captures features in two domains that we're interested in. So we're interested in certain frequency bands which behave differently when the user thinks of each arm, and certain spatial regions which which have more power in them when the user thinks of each arm. So the idea is to extract discriminatory features in these two domains, and how we do that is through this a process known as a spectrally weighted common spatial pattern. So what that does is it takes channel data with 64 channels that we use, and then uses a filter in the spatial domain and spectral domain. So on top right, you see the circles are spatial filters, which parts of the brain are highlighted by that weight, and that and below the frequency filters. So each channel is multiplied by these features, these filters, these weights to obtain the features, and then they're put through a simple neural network classifier to detect whether they're left or right. So the entire process is trained through an offline paradigm initially and then deployed online. So the online detection happens with the ERRP detector, which detects whether the user thinks of his whether the cursor is moved in the wrong direction or not, and that is a separate classifier which is also trained in an offline paradigm. So the results of these will be discussed by Raihan.
For the demo, we stream one sample at a time, and we compute the probability of the user thinking it's right hand or left hand. And we see a bar graph of the probabilities of whether the user is thinking of right hand movement or left hand movement. So when the user thinks of each kind of movement, the bar graph will cross a certain threshold. So if it is higher towards the right hand side, you'll see the right bar graph go up, and if it is on the left hand side, you'll see the left bar graph go up. And when this is detected, the cursor will move towards right if it is if the user is thinking about the right hand movement, and it will move towards the left if the user is thinking about left hand movement. The same is seen in this demo. We examined the classification of motor imagery using two data sets, and it was a total of 10 individuals. So as you can see, using the combination of spectral CSP and neural network, we got good results for we had high accuracy, precision, and recall. However, you can see that few individuals have lower accuracy, like 63.5%, while you can see individual 4 has 99% accuracy. To better this, we used online adaptation. So the testing procedure for online adaptation for the MNI classifier is shown in this table, on the following tables. So the process involved dividing the dataset into 3 parts, each containing equal number of samples. Part 1 was used for offline training, and the base accuracy was tested on part 3. And the classifier was then adapted online using part 2. After the online training, the classifier's accuracy was then again evaluated on part 3 to assess any improvements. So the tables present the difference between accuracy before and after online training on part 3. So generally, there's an increase in accuracy, which is observed, although there's like a minor cost in precision and recall. So as you can see in the tables, before online training and after online training, you can see the accuracy is increasing from for individual 8, it's from 85 to 88, and for individual 9, 79 to 86. And again here, you can see it's going from 71 to 81%.
So the entire project was essentially divided into 3 different parts. The first one was building a motor imagery classifier just offline with SpecCSP and neural network and displaying its accuracies, which Raihan displayed. The second one was building an error-related potential detector or a classifier whose accuracies we didn't show to keep the video brisk, but only if the ERP detector works well will the online adaptation actually work. So building the ERP detector is the second objective, and the third and final landmark is to actually test if online adaptation works, if the accuracy increases when you go from offline to online training with the help of the ERP detector. So the results of which Raihan again displayed and proved that the accuracies actually increased with with online training, and the baseline accuracy was slightly low in some cases, and it increased with online training. The ERP detector enables the online adaptation. So if the ERP detector didn't work well, we wouldn't have good online accuracies. So this wraps up and summarizes the entire project with the 3 different landmarks, with each of them completed successfully. Thank you.